Okay, today at the end of the period, you're going to have to do some work. I have a lot of actually worksheets to come over the next couple of days. And this one today is going to have a chart on here like this one here. Okay, I told you I go over these charts every day, and these different charts are covering different trends. We're going to get the last trend today in a minute, but let's see if we can identify some stuff. All right, just by looking at the chart. We're not very good at interpreting charts. This is not something that is a skill reserved to chemistry. This is something you're going to have on your SATs for your math class. You'll have it on a lot of different standardized tests where you have to simply interpret a graph. A lot of you guys do not, you just guess. If it takes more than one step of reasoning, you don't want to do it, okay? And this takes more than one step of reasoning. If I ask this question first, if I ask you, what trend is this? You can't just look at it and see. You have to think about it. What is this trend doing across the period, and what is this trend doing down a group? Then you got to decide, okay, once I find out, in order to find that out, I have to find out where is my period and where is my group on here. What does A correspond to about the periodic table? What elements are in A? Where are those elements in the periodic table? The ones that are in this bracket, these guys right here. Because a lot of people see this and they say the main trend they see is increasing. Something's increasing. But is it increasing down a group or is it increasing across the period? What do you think? What is A? What is it? A period or a group? So, now it's going to go here. What is A? A period or a group? Kent?
Period.
A period. Because if I simply look at the elements, 3 through 10, they're on the periodic table. 3 through 10 is lithium through neon. Okay? So I have to first decide where's my period, where's my group. Then I can answer the question. It's a three-step process. You don't want to do that. That's work. I got to first figure out where's my period, where's my group. There's my period. It's getting bigger across a period. And my group, the elements like 2, 10, and 18 are all in the same group, and it's going down as you go down a group. So that's the first step. Where's my period? Where's my group? Second, what is it doing across there? And third, which trends fit that pattern? What trend gets larger as you go across the period? Does atomic size do that? Does atomic size get bigger? Now, don't look. I want you to think. As I go, this is the difference. All right. Notice we're already on the third thing in the reasoning process. First is, where's the period, where's the group? Second is, what's it doing across the period, what's it doing down the group? And lastly, what trend does that correspond to? Again, use some common sense. Look at the periodic tables. I go down a group in the periodic tables. I look at my periodic table. I go down a group. What would you expect is going to happen to the size of the atom? What did we learn happens to the size of the atom? It gets bigger, right? This guy is getting smaller as he goes down a group. Can this be atomic size? No. So what trend must this be? That we've only learned a couple so far. What trend do you think this probably is then? Now you can look. What trend do you think this probably is? What trend is going to get bigger across the period and smaller down a group that we've learned about in the last couple of days? Huh?
Electronegativity.
Electronegativity. Yeah, the attraction for electrons. Okay? Now if I look at this graph, by the way, I think these are easy questions. You'll get questions like this most likely right. If I'm just pointing to a single thing on here, that's not a three-step process. I don't really have to think about where he is in the periodic table. I don't have to think about what's he doing as part of the trend, and then what trend is he part of. It's not 3 steps. It's 1 step. I look here. I figure out what number is he. Atomic number is 2. He's 2 more from that, so that's 4. So he must be beryllium. Okay? That's an easy 1-step thinking process, so you usually get those right. You usually stop thinking about it once it takes more than 1 step. All right, and that's what I'm trying to show you here. If we look at this trend, again, I can point to an easy one like this. You see he's number 6. That's carbon on the periodic table. Easy enough. But again, what's this trend doing across a period? What's it doing down a group? All right, as you go down, as you go across a period, these are the periods here. He's getting smaller. What trend do we know to get smaller? Atomic size, right? Okay, and then it gets bigger as you go down a group. Now, believe it or not, I'm not exaggerating when I say this. I've done these now for 3 days. I've shown you these charts for 3 days. Briefly the first day, and then more detail the last couple. And by the time I get to sometime next week, this has actually happened. I'll have people who will tell me which trend this is, electronegativity, atomic size, and I'll ask them why. Because it's green. That's why. They'll remember the color. They'll remember that that guy's green and that guy's yellow, and that's how they'll remember these. It ain't going to be like that on the test. I mean, if you look at the graphs I've got on your worksheets on the test, they're not green or yellow. They're not the exact same graphs, okay? They're not going to be exactly the same. So you have to be able to interpret them. You can't memorize your way out of this stuff, okay? All right, let's get to the new stuff. This is the last trend. It is called ionization energy. All right, let's talk about it. This guy's a very important trend as well. And I will, by the way, show you other graphs that aren't in that same format that happens to be what I get with my, pictures that come with the book or pictures I found on the internet. So they're all like the same exact graph each time. Because you do get, basically attuned to memorizing that stuff. Oh, I see that. It's yellow background. I know which one that is. I see the green. I know what that one is. You want to be thinking about these, not just looking at the colors. All right, what is ionization energy? Well, again, this kind of a word like electronegativity. You should be able to remember electronegativity because it's the attraction for electrons, right? Ionization energy is the energy it takes to make an ion, and we make ions by pulling electrons away from things, okay? So it's the energy required to remove an electron from an atom, and that makes an ion. That's why it's called ionization energy. I asked you to do this with me yesterday. It wasn't fun. I asked you to tell me what the next things coming up here are going to be. And it was like pulling teeth to get you the next word and the next definition. But the sad part is, I wasn't doing that for fun because it's never any fun. It's always a lot of work on my side. But it's the way you should be in every single class. Remember, it's not about chemistry. I know I have to teach you chemistry. I know I have to do that. But the fact is, that chart we just did, interpreting a chart, showing you how to think about a chart, that's more important because it's not just chemistry. Taking notes, sitting there waiting for me to touch on this board and have the next word come up, you're not learning anything. Thinking about what my next word's going to come up, what do you think that next? Well, I'm going to talk about this trend. What's the next word that's going to come up here, Cece? That's right. So we're getting better at this. So we're paying attention. So if I ask you, I don't care if it's a wrong answer, I want you to tell me what the next words coming up are going to be. What do you think the energy required to take an electron is going to do as I go down a group from top to bottom? You think it's going to take more or less energy to remove an electron as I go down a group? Use the one trend we've already covered for 3 days, atomic size. Okay? As I go down, what happens to atomic size in any given group as I go down? What's happening to atomic size? I'm adding an energy level every time, right? So the electrons, all right, down here, would they be easier or harder to remove? This is, again, a multiple-step process in thinking. That's why it's called thinking, not memorization. This is how it differs from your bio class, your history class. I have to first think, what happens to the trend as I go down? Okay. Second, well, how would that affect how easy or hard it is to remove an electron? And therefore, what would my answer be as I go down a group, does ionization energy increase or decrease? Who's ready to give me an answer to that? What's this next sentence going to say? Ionization energy increases or decreases? What do you think, Maddie? Decreases. As I go down, they're further away. You all agree? Absolutely. This is thinking. It hurts. We don't like it. But it's what you'll have to do on this test to get a good grade. Because you saw what happened on the last test when I asked you thinking questions. What guy over there has 2 electrons in the 4p sublevel? I got to think about that. It's not something I can memorize. What's the highest energy level for argon? I got to look into and count down and think about it. All right. How do I draw a shorthand notation? All that stuff required multiple steps. This does too. All right, that's the first thing. Again, I'm not telling you the notes. You're telling them to me. Why? 2 reasons. Who can give me one of the 2 reasons? Why, as I go down a group, it's easier to remove a guy down here than it is to remove a guy at the top. Who wants to give me that? One reason. You don't have to give me both. Justin. The increasing atomic size. Now, listen, your class had a great bad answer. Let me tell you what that bad answer was. The other class I called on him for the previous one, they said because of atomic size. What's wrong with that answer? Yeah, he didn't say it was increasing atomic size. And even that isn't quite enough. I need you to refer to, the AP exam is extremely picky on this stuff. Even saying that atomic size is enough, you have to explain that even further. You have to say, because of the increasing atomic size, electrons are further from the pull of the nucleus. According to Coulomb's law, they're not held as tightly. Right? That would be the whole story. Like that. Increasing atomic size, electrons are farther from the nucleus. And by the way, I meant to ask one of the English teachers, is it farther or further? What do you think? Which is the right word here? I think it would be further also. That's why it doesn't look right. So I'll change that. You can change it yourself. I think it's further. But I'm not positive. I meant to ask somebody. All right, that's one reason, absolutely. And by the way, we're only doing this one trend today. We don't have a lot. I'm going to give you that worksheet. I want that to be finished in class. So you really want to pay attention to that. You've had 3 days to cover this stuff. Okay? Now you know how it goes. I mean, I let you do some practice problems, and you work together. And homework, I don't really grade it. You just this worksheet gets graded, so you hopefully understand what's going on by now. What's the other reason? Give me another reason besides the fact that electrons are physically further from the nucleus. Something else is happening here, Joe. What's that? Shielding. Absolutely. The shielding effect. And I've got a little shortened version of that. Basically, the inner shell electrons are blocking the pull, right? Now, that's not a good definition. Your good definition is in the previous place where I defined it. But I'm just, reminding you that you have to be specific on these answers. You cannot just put down, oh, and my favorite, yesterday I think it was in this class that I got that really good bad answer. The other class had a good bad answer. When we went down a group, it gets, less because of atomic size. You gotta say because of increasing atomic size. In this class, I think I had someone say, oh, why is the atom getting, why is the atomic radius increase? And someone said because the atom's getting bigger. All right, that's a really bad answer as well. Why is that a really great bad answer? It's like saying, I think I used this yesterday. It's like saying, why are you getting fat? I'm getting fat because I weigh more. That's not why I'm getting fat. All right, I'm getting fat because I'm eating too much. I'm getting fat because I'm not exercising enough. Those are the reasons I'm getting fat. Same thing, what is the reason it's easy to remove an electron? It's not because, it's my favorite. In this one, what would an example of that question, of that answer be? A bad answer. I would ask you on the test, what happens to ionization energy as you go down a group? And people would say, ionization energy decreases because it's easier to remove an electron. You see what I'm saying? Why are you getting no points for that? Ionization energy decreases because it's easier to remove an electron. You've just simply redefined ionization energy, haven't you? That's all you've done. You haven't explained why. Those are the reasons why. I know it seems like I'm spending a lot of time on this, but you have no idea. I just took that AP class over the summer. You have no idea how picky people are on that. And you say, well, this is an AP. I know that. First of all, it's honors. All right. And secondly, the same laws apply to your SATs, your keystones. They grade those kind of questions with a rigor that you're not used to. Well, you know what I meant. You can't use the you know what I meant excuse. You have to actually say it. All right? Okay, let's do the period. You should be able to do this one. But I did this in your class. Do period on your own. Fill in what you think I'm going to write for within a period. And I bet you can do it. Write the whole thing. Reasoning and what it does. All right, let's see if you got what I would have put. You got it? Okay. From left to right, obviously, I'm going to say here first. From left to right, what's going to happen to the amount of energy it takes to remove an electron? Well, we know what happens. The atomic size gets smaller as we go across, which isn't what we would have predicted originally. But because it gets smaller, I would say that the amount of energy is going to increase because it's going to be harder to remove an electron. It's going to increase. It's going to be harder. Okay. Why is it going to be harder to remove that electron? Two reasons. One is the fact that it's closer to the nucleus. And again, I'm shortening these up. You could have put, don't erase, you could have put the fact that, explained it further, but I'm shortening them up because by now we've seen that same explanation like 3 or 4 times, okay? So I'm shortening it up a little bit. Octet rule and the decreasing atomic size. You can't shorten up on a test. On a test, you've got to explain it in full detail. But, obviously we don't have to keep writing the same thing over and over again. That gets a little tedious. All right, here's the big but, though. You could put that thing down there. But we have a problem. There are some exceptions that I need to explain. Now, a lot of people notice in my other class, they like to argue a lot. When I had that graph, this chart up here, okay, this is the same chart I had on your paper as well. So when I have this chart up here of atomic size, some people notice that there were guys who actually don't get smaller as you go across. Okay, and if you look at the chart was actually for atomic size in there. Once you get past the first couple of periods, even in the first couple of periods, they don't decrease uniformly. All right, for atomic size or for electronegativity, it's not perfect, but these are different. These exceptions are much different. Look at these exceptions. They happen at a very specific place, and you can see they repeat themselves. There's got to be something involved with this. By the way, I want to show you this for a reason. Okay, this helps to point out. You ever wonder why, in a magazine or a newspaper or in a statement from a bank or whatever, your investments, why do they use charts? What's the point of a chart anyway? Why am I making you learn these periodic trends in a chart? A lot of you probably wonder, why do we have these stupid charts on my SATs? Why do we have to do them this way? There are things that pop out in a chart that do not pop out just looking at the raw numbers. Like, for example, you really have to look carefully at this guy to find any exceptions. And there are some exceptions in here. But you really got to look carefully. It doesn't pop out at you, right? Just looking at the numbers, even just looking at the size of those little circles. But that is obvious. And it's happening at the same spots in the periodic table. I need to explain why going from here to here and here to here. Let's look where they are in the periodic table. I can't pull it up for the people at home, but you guys can see that this trend from what element 4 and 5 happens between beryllium and boron, groups 2 and 3. See them up there? Where does it happen again over here? 12 and 13. Look where 12 and 13 are. Directly below beryllium and boron. They are magnesium and aluminum. See it? What's going on there? And then it happens again over here. And they, again, are in the same place, right above and below each other. I have to explain that. All right? This stuff you might have missed. You might not have seen it. You might not have realized it unless you saw it in a graph format. It's one of the reasons we do graph things. Okay, here's the reason for the exceptions. Let's draw each of those. Let's draw out the orbital notations for, we're just going to take a representative example. We're going to use beryllium, the group 2 elements in 3, beryllium and boron. I'm going to show you, and I'm going to ask you, actually, and tell you to tell me why you think it might be out of order. Something's not right here. Now, first off, I want you all to look over here, and again, I guess you can't see it. I guess I could pull that up. I should have had it ready for me anyway. I'm going to go back to that one. What slide is this one on? I want to come back to it. Well, it doesn't even say. I want to show you that one here anyway. First of all, I want to make sure you understand why this doesn't make sense. Here's beryllium, and here's boron. By everything I've taught you, it should be harder to remove the electron from boron than it is from beryllium. You all agree? Here's the size of beryllium. Boron's much smaller. If those numbers are correct, this is 111, this is 82. Much smaller. The electron's closer to the nucleus. Coulomb's law says it should be a much stronger attraction. Okay? Hold on. Wait. Oh, yeah, okay. Thought that said. Wait. What does it say? Okay, first I thought I said Fishman, which there's no Fishman. Then I thought I said Marshman, which there is a Marshman. But it actually says Freshman. Freshman, right? So apparently we have a freshman, Jacob. Yeah, you can get that later. All right, so this guy is much smaller than him. Shouldn't it be harder to remove an electron? Isn't he closer to having an octet? Wouldn't he not want to lose an electron? Aren't those two reasons going to apply here? What is going on? I don't understand it. Why? Well, let's take a look. When we go and draw beryllium and boron, we get this. Everybody agree? Whoops. We get this. Oh, no. Sorry. 1s2, and we have the arrows underneath it. Let's do those. No, that's not right. No one would have trouble writing this. We've all done this in the previous chapter. And I say this not jokingly, although a lot of the grades in the last chapter's test weren't great. It wasn't because of this. You didn't lose your points because of this. You lost it because of the front page in most cases. Okay? So you do all know how to do that. Everybody would be able to do that. Now that I've written those out, can somebody tell me, even though beryllium is this big and boron is only that big, why is it easier to remove this electron than it is to remove that electron? Okay.
It's not paired.
Okay, all right, filled is one of the things. Yeah, this is a filled sublevel. That's one good reason. This guy only has one electron inside. Things like to be filled or basically filled or half filled. Remember, we talked about the exceptions in the D sublevels where you've got 5 and a guy who is like this, and he was at one short. Actually, it turns out that the S that you would have thought would have been paired up isn't. That electron's over here. It's better to have a half-filled sublevel or a completely filled sublevel. It's just more stable. Don't ask me why. I don't know. Somebody probably does. Some quantum mechanics guy. So yeah, that's good. One good reason. Filled things. This is filled. This guy is only got one electron. What's the other reason? Where's that electron coming from versus where that electron's coming from? What do you think? That we also know has to do with stability and happiness for those electrons. Well, this guy's coming from a P, right? Is the P shape as stable as the S shape? No. So for both of those reasons, removing a guy from the P shape versus the S shape is going to be a little bit easier. Removing a guy that's filled is going to be a little bit harder. Okay? All right? So I would expect that even though the size of this atom has decreased, it's actually a little bit easier to remove this electron than it is the other ones. For two reasons. One, these are reasons for the exceptions. All right? Filled or half-filled sublevels tend to have extra stability. I've mentioned that before when we talked about the exceptions, which we didn't do a lot with the exceptions. I told you that's not a big deal. All right, we don't have. Matter of fact, I just saw some of the stuff on the AP exam. They don't really stress that very much. They're not making you memorize which ones are exceptions. You're just supposed to understand it, why it would happen if it does happen. But it has to do with the filled or half-filled sublevels, and that's one reason. And here's the other reason. The P, in this case, and the S don't have the same stability. Different orbital shapes have different stabilities. Now, this is crazy, but I want you all to understand something. on the worksheet I'm about to give you, okay, I'm going to ask you a specific question about these guys. Worksheet you're going to get in a minute. You know what some people will write down, even though I'm saying it right now not to do this. Some people will write down as the answer for the explanation. Filled or half-filled sublevels have extra stability. Different orbital shapes have different stabilities. Why will I not accept that for full credit? It's exactly what I wrote here. Why won't I accept it? If I say specifically, if I ask you specifically, why is it easier to remove an electron from boron than it is from beryllium? Somebody give me a good answer, not just rewriting verbatim my notes. Who can give me a good answer? Two parts to it. One sentence. Give me one of the sentences. Come on, you have to help me, because if you don't do it, I don't know what mistakes you're going to make. Some of you out there are just saying to yourself, well, I don't understand why I can't just say that. Okay? It's not specific. Give me the specific answer. Somebody. Come on. Anna.
Because boron only has one electron and 2p, and it makes it less stable.
Okay, so the P shape for borons, one electron, is less stable than the S shape, would be one half of the answer. And what's the other half? The fact that the boron's electron is not filled, not on a filled sublevel or paired up. These guys are. So you would say specifically which one you're talking about. In other words, just saying different orbital shapes have different stabilities, you're not implying to me, you're not imparting to me your knowledge that it's the P that's less stable than the S. But you know I know that. No, I don't. This is what these kind of test questions are like. If you think I'm making this up, sometime in the very near future, because almost all of you are in AP Physics, sometime in the very near future, you're going to get exactly these same kind of questions on the AP Physics exam. Guaranteed. I'm not just preparing you for chemistry. This is the way you'll have to answer those. Okay? And they aren't going to accept a verbatim generic statement like I have in my notes here. They're going to want you to explain specifically why this electron is easier to remove than that electron. Not, in general, why these electrons are easier. I know. I'm not arguing. I would have accepted in the past more generic statements, but I've learned from this class, specifically, not to do that. I've learned I have to be more picky about that stuff. All right, so real quick, you're going to see on your worksheet, you're going to have about 15 minutes to do this, which is plenty of time. You're going to see on that worksheet questions with graphs like this, where I'll ask you to interpret, is this, which trend is it? What does it do across a period? What does it do down a group? If I ask those questions, you've got to know where the period and the group are. You've got to be able to do that. And notice they're not going to look like my other graphs all looked, right?
Can we get past the next period?
In a minute. All right, give you 1 second. All right, also on this test will be questions like, and I want to kind of do this with you real quick. Say I gave you 3 elements. Let's just call them A. Nope. Let's try that again. Let's call them A, B, and C. And I asked you, who has the highest ionization energy? Who do you think? That's the kind of question I'm going to ask on this, too. Who's got the highest ionization energy? Who be the hard? Well, again, it requires thinking. If I just ask that question, you're just guessing. If you tell me one, you don't want to be a logical guess. Either this guy or that guy, right? Is anybody going to put that guy down? Probably not, because he's in the middle. So logical guess would be either A or C. But here's how you have to think about it. Number 1, what is ionization energy? Well, it's the energy required to remove an electron. Okay, second, I rephrase that in my mind. Who would it be harder to remove an electron from? This guy over here who's large, or this guy over here who's small and close to having an octet? Y'all agree it's this one? So it takes several steps in the process. If I ask you, who's the better metal? Again, it's going to be a guess unless you look back at your notes and see what is a metal. What does a metal do? A metal loses electrons. The metal loses electrons. Which of these three guys, is going to be more likely to lose electrons? You all agree it's this guy over here because he's a larger atom, electrons are further from the nucleus, and he's nowhere near having an octet. Got it? That's what your things are. You're going to have to finish this worksheet.